Hello, this is a talk about the joint work with Pankaj Agarwal that is about to be presented in SoCG to 2023. And it's about instance optimal kernels. So this goes back about 2 decades to the beginning of the millennium, roughly 2000. Where we studied the following problem. You're given a point set and you're interested in capturing its structure with a small subset. So somewhat informally, what you have is you take the convex hull of the point set and you shrink this convex hull by a bit, and now you want to find the small subsets that its convex hull contains the inner polygon. And surprisingly, in a joint work with Kasturi Varadarajan, we showed that there exists a subset of constant size that does that. And using that, we could solve various optimization problems. Now, time had flowed, pulling its regular trick. And 9/11 happened, and the US invaded Iraq, and so on. I will not go through the history over the last 2 decades. It's all written in the history books. It's written there in blood. But fortunately for us, nothing happened for 2 decades until Wang et al. In 2021 asked the following very natural questions. Can you find the minimal size coreset for a specific point set? Right? Namely, you're given the input point set and you want to find the smallest subset that have this desired approximation property. And then they provided a positive answer. The running time was cubic time. But unfortunately, the definition of this kernel was not quite our definition. So in terms of the original definition, what they proved is that the kernel is of size smaller than the kernel, the optimal kernel with parameter epsilon over 3. Now, the important thing to remember here is that the kernel gets bigger as the parameter epsilon shrinks. So this, you can think about it as if you want, a tree approximation in some sense of the problem. But of course, that's not very satisfying because the running time is not very good. In the follow-up work, Klimenko and Reichel improved the running time to being sub-cubic, and their running time was, and their approximation was better. It corresponded to coreset, optimal coreset with parameter epsilon over 2. And of course, what we want is the kernel, the real kernel of size epsilon, right? And when do we want it? We want it now, which means with a fast algorithm, near linear if possible. So let me first tell you about a related problem that is similar in nature. And we are given a point set, and I give you a polygon that is contained in the convex hull. For example, in this case, it would be this green triangle inside. And the problem is to find a minimum subset of the points such that the convex hull contains the inner polygon. And even this problem that looks quite innocent is not obvious how to solve. And in particular, even this simple example on the slide shows that the natural conjecture that the optimal solution is formed by the vertices of the convex hull is not correct. So how to attack this capture the polygon problem? And the basic idea is that we are going to take this inner polygon, and for every point outside it, we are going to compute the region that it can see of the boundary of the polygon. It's easier to work in the parametric space of direction, so I pick a direction. My polygon has a tangent in this direction, and the points see the tangency point if the point is on the other side of the tangent for this direction. So what happened is that now that every point now corresponds to a hat-like shaped, a clown head shapes like, which in this parametric space of direction corresponds to an arc. So now it's easy to verify that capturing the polygon boils down to the following problem. I give you n arcs covering the circle of directions. Find a minimal subset that covers the whole circle. And the natural algorithm is the greedy algorithm. You pick some arc and you start going clockwise, going as far as you can, add this new arc to your coverage and repeat this process until you get back to the original arc. It's easy to argue that this provides you with a solution which is of size opt plus 1. And in fact, it's the optimal solution if the starting in arc is one of the arcs in the optimal solution. So it turns out that being a bit clever or a bit careful, you can first compute a set of n over k starting arcs, and then you run this greedy algorithm. Now, the greedy algorithm, if you think about it, is performing these k queries of how far can I go for each arc, and we can implement each such queries in log n time using data structure magic. So overall, you get n queries overall, because we have to try n over k starting arcs over each one requiring k queries. So we get running time n log n. And this algorithm is of course known. It was known to us initially, but the referee pointed it out. And it was done by Lee and Lee in 1984, but our solution, we believe, is simpler, but simplicity, of course, is in the eye of the beholder. Let's go back to kernels. So our problem is that we have a set of lines, and we look on the upper and lower envelope of the lines, and now we have an approximate upper envelope. This is the red jagged line in the slide, and we have an approximate lower envelope. And our purpose is to find a minimal subset of lines such that their upper envelope separates the approximate envelope from the exact envelopes, right? Namely, the upper envelope is separated by the line from the approximate upper envelope, and the same thing for the lower envelope. And the question is how to find a minimum number of lines to do that. Now, it turns out that it's easier to think about this problem instead of in the dual, which was a setting I described in the previous slide, but instead thinking about it in the polar, using polarity. So I'm not going to define what polarity is. It's essentially inversion and duality combined in some sense. So the important thing is that inverts points to lines and lines to points. And in particular, for our problem, once we do the inversion, the problem that becomes the following. We have a set of lines. We have the origin. The face containing the origin is this yellow polygon of this arrangement. And then we have this star-shaped polygon around the origin, which is this red polygon, which contains the yellow polygon. And the question is to find a minimum number of lines such that they separate the yellow polygon from the red polygon. So the question is how to do that. And intuitively, this looks very similar to this arc coverage problem, because take every line, its portion inside the red polygon. It might be, unfortunately, several segments. And now pick a minimal subset of those segments over all lines that essentially blocks the yellow polygon from seeing the red polygon. And in fact, this can be made to work. The big problem here is that one can show that the number of such fragments of lines overall can be quadratic. So the naive algorithm doesn't quite work, but it turns out that being a bit more clever and running first a greedy algorithm, we can in fact get a subcubic running time. So we get the following result. We can compute an epsilon kernel in size k over of size optimal kernels times n log n. Since the optimal kernel is bounded by 1 over square root epsilon, and we consider epsilon to be a constant, effectively this is n log n running time algorithm, so we got what we wanted. We could, of course, withdraw and declare victory, but like the US did, in Iraq, we will stay much longer than is wise in this talk. And maybe let me first give you a feeling, why do we get this, why is the explicit problem representation is quadratic? So consider those two, those three lines, think about their upper and lower envelope. Now think about this average of the envelope. It's this green line in the middle, and the surprising thing is that this level is not convex, right? It can be up and down. And this in particular implies that the approximate upper level, which is this purple line in the slide, in fact is not convex. It looks essentially like a chain of mountains, essentially. And then it's very easy to add a set of linear number of lines such that every line stubs a linear number of mountains, so you get quadratic number of segments, which means that if you're trying to cover the mountains by fragment of segments so that the red curve is vertically blocked from the purple curve, you're getting this interval coverage problem, but you're getting it with quadratic number of intervals, and that's too expensive. But fortunately, by essentially pre-processing this mountain range to the right type of queries, we can do some range ray-shooting queries and so on. We can get the faster algorithm I mentioned before. Okay, now it turns out that the original paper in fact defined a different kernel. It defined a weaker notion of a kernel, which somehow magically worked there. And the concept is that what we really want in the epsilon weak kernel is to find a subset of the line such that for any x coordinate, the vertical extent, the distance between the upper and lower envelope of the lines you pick, is larger than the extent of the approximate envelopes, right? It's a bit bizarre. In particular, it implies that the set of lines, the extent, the region captured between those two envelopes can be above the approximate envelopes. And this made the problem much harder, because now when you compute the optimal solution, you have to deal with the interaction between the upper part and the lower part of the envelope, which make it harder. Nevertheless, we were able to provide a relatively efficient algorithm. We showed how to compute it in quadratic time, or almost quadratic time. And to appreciate this result, maybe let me mention that our initial algorithm for this problem had running time n to the 7th, so getting the running time back to quadratic was quite satisfying. And again, this requires some ideas, and see the paper for details. Okay, another concept that we played around with was this notion of a core. So the basic idea is that you have a point set, and for every direction, you can look on the two tangent planes to this convex shape with these directions. And now what you do, you take this slab and you shrink it, right? Let's say a factor of 1 minus epsilon. And you take the intersection of all these slabs, right? So you get the region, right? You get this region. It's a convex region. We call this region the core. The core is essentially, intuitively, is a shrunken copy of the original shape at some intuitive level. And it turns out that it's a very neat definition of this notion of how to approximate a shape. Of course, in some sense, it's similar to this John ellipsoid. But the John ellipsoid, of course, gives you only a much weaker approximation. This is a much better approximation. In particular, if you compute the core, which we can do in log n time, then you can now play the catch the polygon game with it. And it turns out that if you do that in log n time, you get a kernel of size with parameter epsilon over 4. So it's not the optimal kernel, but the running time is very good. There's no dependency on the size of the kernel, which makes us happy. Okay, here's a summary of the results, of the relevant results. And as you can see, we start with the result. We have this linear running time algorithm to compute the kernels, but they give us only a bound on the kernel side in terms of epsilon. As far as optimal kernels, our result now provide near linear time algorithm, where previously only quadratic time algorithm were known. And we also solved this weak kernel variant. Okay, let me mention another variant of this problem, which is the Hausdorff distance version. So here you want to find the smallest subset that have Hausdorff distance at most delta from the original shape. And it turns out to be a natural heating set problem where for every direction you take the tangent in this direction to your shape, and then you push it in by distance delta. This gives you a half plane, and you need to pick a subset that hits all the half planes. And so that's what we want to do. And what we can show is that we can compute the optimal such subset. And again, we can do this in near linear time. So we get the following result for the Hausdorff distance. The previous results were by Klimenko and Reichel, and now we get a similar result to what we had for the kernel version. Notice that this Hausdorff problem has an easy two approximation from previous work. So if you want just two approximation, the previous work might be good enough for you. Okay, a few open problems. For 3D, we know the problem is hard. Can we do some approximation, interesting approximation, maybe a pitas? I don't know. One needs to figure out exactly what's the problem there and what can be done. And the running time of size independent of the kernel, even in the plane, we are still not quite there. It's not a super important problem because the kernel size, again, we think about k epsilon as being a constant, but still, it would be nice to remove this abomination from the running time. That's it. Thank you very much.